Hi, folks. Welcome to another episode of YFTT. I have Jason with me here, and we're going to talk about how we're speeding up YSQL aggregates using pushdowns, where you ship, the execution of the query to where the data is, as opposed to pulling data to where the query is being executed. So very interesting, very insightful, very exciting talk. So looking forward to it. Hope you guys are too. Anyways, in the meanwhile, if you guys have questions, just feel free to drop it in the LinkedIn comment box or, join us on our community Slack. And we'll get started in a few minutes. Please stay tuned. Hi, Jason. Thank you for taking the time.
Yeah, no problem.
So you're based out, just for our viewers or anybody that may have joined early, you're based out of the San Francisco Bay Area. Is that right, Jason?
Yeah, I'm actually in the office right now.
The office in Sunnyvale. That's fantastic, man. Fantastic. And you've been working on a lot of the YSQL features, right? Like maybe you can talk about a couple of those.
Yeah, I have two past YFTTs. One's on the chain indexes, one's on the index backfill for YSQL and YSQL.
Awesome. And what are you looking at now? That's cool and interesting.
Right now, this is actually very fresh out of aggregate pushdown work I did. I'm still tuning it a little more, but
fantastic.
Yeah.
Fantastic. So really looking forward, fresh off the oven.
I might go on PG-15 work.
Oh, very nice. I rebased to PG-15. That's awesome. That's awesome. Yeah. Heavily asked for by a lot of people. So yeah. So there you heard it, folks. Jason's going to go help out on that. Awesome. Fantastic. So if I remember right, you have a few demos also showing the difference between doing a push down and not doing a push down. Is that right?
Yeah, that's most of the demos.
Fantastic. Yeah, I think that's, sometimes it's easy to underestimate just how much of a win you can get with pushdowns or with not moving data, right? Like, and just executing in place and reducing the amount you move. So yeah, it'll be quite interesting to see.
Yeah, particularly when there's a lot of network, like there's a distance between the nodes.
Yeah, that's right.
So network latency is higher.
That's right. That's right. That's right.
We also take a look at some PG performance comparison.
Ah, fantastic. So yeah, for those of you folks who are online listening, well, we are starting to get to work just like Postgres. So in terms of performance, in terms of the query plans, as long as the data set is local, and transparently switching into distributed execution when the data gets big and starts moving around and splitting and sharding and all of that stuff. So they were starting to compare a lot more with how you would expect PG Postgres to work. So yeah, this is going to be really interesting, Jason. Really interesting to see.
Shall we get started?
We still have a minute or so. I think we were just early on the live cast, okay, because of the technical issues we have with the LinkedIn live cast that we've had in the past. But let's give it another minute or so and we'll get started, Jason.
Got it.
All right. All right. Let's hopefully folks are streaming in. Hi, everybody. Welcome to another episode of YFTT, Yugabyte Friday Tech Talks. It's a talk for engineers by engineers. And this week I have Jason with me. Jason, why don't you quickly introduce yourself and we will kick this show off.
Hi, I'm Jason. I've been at Yugabyte for over 4 years now, and past things I've done include collocation, chain indexes, index backfill, and then this talk I'm doing about aggregate pushdown.
Awesome. Thank you, Jason. I think just like we talked about a few minutes before, folks, this is about speeding up aggregates with pushdowns. Pushdowns are when you move your execution closer to data, as opposed to moving data closer to where your query is getting executed. It generally is much more efficient to move execution to data because there generally tends to be a lot more data, right? So, but don't take my word for it. Like, let's listen to what Jason has to say. And if you guys have questions, just feel free to ask in the LinkedIn comment box. Just throw in a question. We'll take a look and answer. And you can also join our community Slack at yugabyte.com/Slack, right? And ask questions there as well, and we'll get to it. So without further ado, maybe let's kick it off, Jason.
All right. Okay, so since this is our first talk, YugabyteDB talk on pushdowns, I want to ask, what is pushdown exactly? It's when we perform computations at the storage layer rather than the query engine layer, and this typically results in less network traffic. Let's see an example. If we don't do pushdown, then when we send a request like a select, for example, then we get responses of the data from the storage layer and then run any computations we need on top of that. But with pushdown, instead, when we send a request, computation will happen directly where the data is. And this can result in less data being sent back in the response, which would mean more performance. There's different types of pushdown. One example is index key comparators. For example, if you want to select from a table and then you have a filter where index column greater than 10, then we could potentially use this information on the storage layer side to efficiently seek to the number 10 and then take any rows that are after that. This depends on whether the column is ordered like ascending, descending, or hash. So in case it's a range partition, we can do this. In case it's not, then we can't push this down. But the alternative is expression pushdown. That would come to save that case, where arbitrary expressions such as 10 column plus 5 greater than 15, or even like square root functions, these can be pushed down to the storage layer, and then the filters can be computed, and then we could potentially return less rows back. Another example is distinct pushdown, where in some cases the distinct can determine how we execute the scan on the storage layer side. We will have another YugabyteDB about this in a couple of weeks, so I won't go too much detail about this one. And today's talk is going to be about aggregate pushdowns, where aggregate functions such as sum can be computed on the storage side. And then this can result in less rows being returned back. So why do we need pushdowns for aggregates? It helps performance very, very much, such as lower latency of queries and lower CPU consumption. And how does that happen? Well, we're moving aggregation closer to the data instead of shipping the data back and then aggregating them. Imagine how much data is getting compressed, or aggregates typically take a lot of input and then output something very small. So imagine having to ship all that data back if we weren't doing pushdown compared to shipping back the small result instead. It means we would cut down on the network transfers and also potentially RPCs. Also note that this talk is about YSQL because aggregate pushdown is only implemented in YSQL for now. So now let's move into some examples. Select sum from some column, we'll do a pushdown.
So just to understand before you go to the second one, Jason, so let's take the first example. You're saying select sum of a column from a table. And without a pushdown, it's going to fetch all the values for the column and add it where the query is being executed. And with the pushdown, it's actually going to send it to where the data resides, or like and do the aggregate. And at the highest level, when I just think like a layperson, it sounds like they'll do roughly the same, but you're going to tell us why it's different. Is that right? In subsequent slides.
Yeah, we'll get to that and see.
All right. Sounds good. Let's keep going. Yeah.
Yeah. Other aggregates such as average are also supported. We can also have some average of the primary index column with a condition on that primary index. So this would become like a primary index scan. Same thing if we do it on the secondary index column. This would be a secondary index only scan. And you can also do it on some column where you have a secondary index condition. So this will become an index scan. So let's start with the first example, which is a simple one of a select sum from table. So without pushdown, you would ask the storage layer to fetch the first batch of values of the column C. So C1, C2, all these C values. And because of the paging size defaulting to 1024, we would have to ask again, so send another RPC to fetch the next batch of values, and so on until all the values are fetched. And on the query layer side, we would be accumulating and computing the sum. With pushdown, you can just ask the storage layer to fetch the sum directly, and then it would compute it and just send that one single value back. A lot faster and a lot less traffic over the network. The other sequential scan example was average. So this one, I wanted to get a little more involved in a specific example where I create a table that's split into two tablets and then insert values from 0 to 4,000 and then select the average. On a previous version, such as 2.16.7, we didn't support pushdown of the average aggregate function. So the explain would look like this, but in 2.19.2, we do support it. So the explain looks like this. The thing to notice is that it has partial aggregate, which signifies that it's using the aggregate pushdown. Let's see an example. So here, the top left, I have 2.16.7, and then the bottom left, I have 2.19.2. And these are Yugabyte local clusters on a GCP 4-core 16 gig machine.
And 2.16 does not have pushdowns, and 2.19 does, correct?
For the average function.
For the other particular example, yes, got it. Okay.
On this side, I have, the right side, I have logs for the Postgres logs for both versions. So let's set this session variable on so that we can see some more output in the logs. This will tell us how many RPCs are being sent out. Let's do the same on this side. Okay, and then I'll run query on the top. So you can see the aggregate is not doing it doesn't have partial aggregate, so it's not doing the pushdown. And then let's see how many RPCs this one sends. So that's 1, 2, 3, 4. And if we do the same on this side, it has partial aggregate. And then the logs, we have 2 RPCs. So why is it 2 instead of something like 1? Well, let's go through the flow.
Okay.
So this table has 2 tablets. I'll just call them T1 and T2. So first, we send the request to the tablets. So notice, since there's 2 tablets, we'll send 2 RPCs. And that's where the 2 RPCs are coming from. Then on the storage side, we'll be computing the sums and the counts. Then we send those sum and count back, and then finally compute the aggregate. And we have to do it this way because average is a little tricky. The counts might not be the same on both tablets. So we just saw an example of a sequential scan, and that's a one-step type of scan. Same with primary index scans or secondary index only scans, and also secondary index scans when they're on a collocated table. But there's also another variant called a 2-step scan, which means we'd first go to the index, and then we'd have to use the results to go to the table. And if you can imagine, this would be less performant because going to the index would not be using the pushdown, the aggregate pushdown. It only when we go to the table, we'll be doing the aggregate pushdown. So let's move on to the next example, which is a primary index scan. So in order to activate something like this, you'd have a primary key, I'll just insert the same rows, and then have a condition on that primary key. So the explains look a little different. It says index scan using the primary key, but again, you can notice it says partial aggregate once using the pushdown. I can also show this one. This one had 2 RPCs. So why is it less than last time? Because this time I didn't create the table with a split at tablets. And since this is YugabyteD, it defaults to 1 tablet for the table. Let's do the same on this one. With the pushdown, since it's only 1 tablet, we're only doing 1 RPC this time. Okay, now with the secondary index only scan, I'm creating an index on the table instead of having the primary key on the table. And then it's the same exact filter, but this time we're going to do an index only scan. So it's only going to go to the index tablet, and it doesn't have to go to the tables tablet. Again, the partial aggregate marker tells you it's using the pushdown.
So this is a pushdown on a condition on the index table, right? Or the index. Yeah. So
yes.
the pushdown is going to push down both the average as well as the where clause.
Yes, the where clause would be the index key comparator type of pushdown.
Yep, got it. So
average would be the aggregate pushdown.
The aggregate pushdown. Got it. Yep.
Okay, so we can see this one too. So this one used 2, because it's not using the pushdown. You can see there's no partial aggregate in the explain. And this side, only 1. With the secondary index scan, this would be the 2-step scan. So the way we can force a secondary index scan is by having the average on the column that's in the table but not in the index. So B is in the index, but A is not in the A is in the table and not in the index. So that's why we're doing an average of A and a condition on B. Again, you can see partial aggregate to determine if the pushdown is happening. Let me reopen the log because it rolled over. So this one has 1, 2, 3, 4. And then this one with the pushdown. This one also log rolled over. This one also has 4. So why are they both 4? So 2 of the requests are to the index and 2 are to the table. And index ones, they will be identical. It's only when the table request that the pushdown happens. But for right now, the table requests are sending conditions that we're looking up using the results from the index scan, which keys to look up. Right now, we didn't optimize that away, so we can get away with, for example, 1 scan. So the best we could do here might be like 3 RPCs, but right now that's not optimized away yet. But at least the difference is that we're returning the responses of the table requests will be smaller because we're only returning the aggregate result instead of all the data back. We'll see this in an example.
Yeah, makes sense. Makes sense.
Yeah.
Before we go there, one question that Jim asks is, does this or any of this help with count aggregate?
Yeah, count is one of the earliest supported aggregate pushdowns. So yes, count is supported.
So count is already pushed down, I think, to answer Jim's question. So the answer is yes, Jim.
Been supported since like 2.0 2 at least.
Got it.
Very old.
A while, forever. Got it. Yeah. Let's keep going. All right.
Right. Yeah. So with these performance demos, I'm going to explain my setup first. So I'm using GCP C2 standard 4 nodes. They're 4 cores, 16 gigs of RAM, Alma Linux 8 OS. I have 3 nodes. They're in replication factor 3. In 2 are in the central region and 1 is west. And the default leader preference is on the west. I created a table space called leader central so that I can force some of my tables or indexes to have their leaders in the central region. I also set timing on for the performance, see the performance, and this macro called run that will explain a query and then also run the query. So first, let's look at the secondary index scan performance. I choose secondary index only scan because it hasn't been supported. It was not supported until 2.19.2. And so we can see a difference between 2.19.0 and 2.19.2. I created a table, demo 1. It's going to have numbers 1 through 50,000, and also this text column. That's just a really giant string of 10,000 characters of A, concatenated with the number G. Create an index on the 2 columns, and the index will be on that central region, whereas the table leaders are going to likely be in the west. And then my query would be the max aggregate on this column T. And then I'm just chopping off and getting the right 10 characters of that. And then an index condition to force an index scan. I already created the table and the index, so because it takes a while. So I'll just run the query, but here on the right side, I have 2.19.0. The left side, and then the right side is 2.19.2. So now I set the query so I can run, see how long it takes. The index only scan, notice how it doesn't have partial aggregate on this. On this side, it has partial aggregate. So this one already returned. It took only like 185 milliseconds. But this 2.19.0, it's without the pushdown, it's still taking a while. It's still not even done. 24 seconds.
24 seconds. Yeah. Wow. That's quite a speed up.
And also we can do this on PG16. I just installed PG16 on one of the nodes here yesterday, and then you can run the same thing and just get rid of the Yugabyte specific syntax, which was the table space syntax. And yeah, let's try running that. So here.
So this is Postgres, right? You're running this now.
Yeah, the upstream vanilla Postgres.
Postgres
SQL 16.
Okay.
So let's set the query and then try running this one. So it's running a sequential scan because it believes the sequential scan is faster. It still takes 7 seconds.
Wow. So
we can try
7 seconds on Postgres versus 185 milliseconds on YugabyteDB. Yeah.
Yeah, and the Yugabyte one is we're sending network requests across from I'm connected on the US West node, and it's going to communicate with the indexes that are the indexes in central region. So even still, it's faster.
Yep.
And just to prove that, like, even if I use an index scan here, Postgres still takes a long time, even though all the data is local on that same exact node. It's still 7 seconds.
About the same. Yeah, about the same. Got it. That's awesome. So Juan has a question. Are pushdown aggregates parallelized yet?
Yeah, normally, like I showed in the flow previously, when we do parallelize the request to all the tablets. So fan out the request to all the tablets, and then yeah, the results will come back in parallel. This has also been around since a long time ago, 2.2.
Got it.
Or before that.
Yeah. So the answer is yes, 1. All right, let's keep going.
Yeah, another demo, secondary index scan. So even though secondary index scan is the 2-step type of scan, it's still more performant today because of the data we return back. It is smaller. So in this demo, I'll be using 2.9.2 only because I can use this session variable to manually toggle whether I'm using pushdown or not. Yeah, and this is a secondary index scan because my index doesn't have the T column. So I'm going to run this on the 2.19.2. And again, like before, I already created the table and the index. So without enabling the index pushdown, it takes a really long time. It takes like over a minute. So I'm just going to cancel this right now, turn it on, and then you can see how fast this one's only 4 seconds compared to the minute that without pushdown would take. I don't know if are people satisfied with the answer or just take my word for it?
Yeah, no, it's great. Yeah, it's great.
Yeah, I also want to show a variety of situations that aggregate pushdown can handle. So you can handle a variety of types. For example, here I have int2, int4, int8, and float4, float8. So you can do aggregates on these types. And then again, I already created the table for this, so let's try this one. Okay, so notice that both for 2.19.0 and 2.19.2, this is using sequential scan, and this one doesn't have partial aggregate. So why is it not using the aggregate pushdown here? It's because of this sum of I8. Today, for some reason, we're not supporting the I8, int8 type for aggregate pushdown. So if we remove that, then it should work fine. So now it's using partial aggregate and it's much faster. So even this side, it's still not 2.9.0, it's still not done getting all that data back. And you can also run like all these different functions on these types as well. And they all work out. This guy's still taking a long time.
Quite a bit of difference with and without. Oh my God.
Yeah, this one's also going to show the different functions we can do, but this time the difference is that I'm using it on a split index. I split the index demo4 into 5 evenly split tablets. Again, the index and table have already been created. Oh, looks like it finished. It took over a minute. But let's run this one now. So this, so this demo4 was partitioned into 5 different tablets, and it still works. I can actually show that demo4 index. Looks like I'm having authentication issues, but that's fine. We didn't have to look into that. Okay. And then the one more demo is you can mix with other pushdowns, such as this is the A is on the index, so this would be an index key key comparator pushdown. The square root is a expression pushdown, and then this B is on the index, so it's an index expression pushdown, and the C mod 10, this one would be on the table, so it's an expression pushdown to the table.
Just a general, yeah, it's not on the index, it's just another column.
Yes, so again, I already created the table, and then the explain tells us, like I said, index comparative pushdown, remote expression pushdown, remote table pushdown, partial aggregate push, so which means aggregate pushdown, and so, and then the values here. You can try the same thing on this side, maybe. And so the difference is it doesn't have partial aggregate, but it takes around the same amount of time, nearly, because this is the two-step.
Yeah, 1.6, 1.7 seconds versus 1.23, yeah, something like that.
Yeah, this is the two-step secondary index scan, so that's why the performance difference is not as great, not as big.
You gotta go to the index first, and then you gotta go to the primary table again, right? Yeah.
Yeah. Okay, now that's pretty much it for the demos. Just some observations and limitations. First is aggregate pushdown is not needed for temporary tables because temporary tables, the data is already local. We're also not supporting window functions because with window functions, it's computing aggregates, but also all the values are returned anyway. So there's not much we can do there. With collations, if we're doing string aggregates, and we do support like string and min-max, it can't be if the collation is somehow complicated, because we're gonna, the sort order is gonna be kind of different down there. And if any of the conditions, the filter conditions, for example, the where clauses, like conditions, can't be pushed down, then we need to return all the rows because we need the row values for the context to value the condition locally. So if we're going to return all the values anyway, then it defeats the purpose of the aggregate pushdown. Though note that there is a very specific case where if you do an index scan, the two-step scan, and then for the index filter that we have to evaluate locally, that we can possibly still do the pushdown when we're going to do the table scan, but it's not implemented today. And then some future work that we can do. Right now, only count, sum, min, max, and average pushdowns are supported, but possibly there can be more aggregates we support, though some aggregates such as like array ag or JSON B ag, they can't be supported because there's not much point in supporting them because they're not making the data smaller. They're just concatenating about a bunch of the values into one bigger value. Distinct and order by inside aggregates currently is disallowed. We can possibly work on that at some point. Same with group by, and gene indexes currently aren't doing any aggregate pushdowns.
Awesome, fantastic.
Yeah,
fantastic. Yeah, thank you. That was really, really informative, especially like how powerful pushdowns are in terms of the latencies they can deliver, and also the aggregate CPU would drop because you're not moving as much data, serializing, deserializing, etc. And especially nice touch on showing like for some of these applications, like how we're going up against Postgres's performance, right? Because it's the same code base and we're starting to unlock more and more of the performance. So that's really awesome. Let's see. I don't see any more questions in the on the LinkedIn box. Like, feel free to ask questions, folks. Even afterwards, you can join our community Slack. It's shown right there, the URL, or was shown, yugabyte.com/Slack. And Yeah, yeah, let us know. You can join us again in a couple of weeks, once again, for another episode of YFTT. Until then, see you guys. Thank you.
Thank you.
Yeah, thanks a lot, Jason. Really appreciate it. It was really, really crisp and very nice demos. Really liked it.
Yeah, even I was surprised at some of these numbers performance.
Yeah, makes sense. It's Postgres just sets such a high bar. It's often tough to meet it, let alone beat it. So it's really amazing to see.